Good morning, Lower Six. Hopefully you have now had a chance to have a look at some of the optimisation questions, and I've put all of those correct solutions into the collaboration space. So make use of that and do have a go at doing all of your corrections. Let me know if there's anything that you're still not clear on. So we've done lots of differentiation recently. Now we're going to move on to integration, which is really just the reverse process. So to start with, we're going to have a think about if the gradient function of the graph is dy by dx equals 2x, what could the original function have been? You might like to pause the video at this point and just have a think about this yourself. So what kind of equations would have given us a gradient function of 2x? Well, it's got to have come from y equals x squared. But is that the only graph? Well, no, it's not, because we don't know whether there's a number on the end. It might be y equals x squared plus 1, it might be y equals x squared plus 3, it might be y equals x squared minus something. So in fact there's a whole family of graphs that would have a gradient function of 2x. And so we say that it's y equals x squared plus something. We usually put a c on the end for the something, and that's known as the constant of integration. And that plus c is important, so you would usually be allocated a mark for putting that on. So find the equation of the family of solution curves which have a gradient function given by f dashed of x equals 6x squared. Well, our original function then must have come from an x cubed equation. If I differentiate x cubed, I would get 3x squared. So I really need to have another 2 here, and now that would work. Plus a possible number on the end, plus c. Now when you start playing around with these sort of things, you think, well, actually we could explain this as a rule. But basically what we're doing is we're increasing the power by 1. And that's the first thing you need to do each time. So to reverse differentiation, we increase the power by 1. And then we need to divide by that new power. And then finally put plus c on the end. So let's see the sort of questions we could get. Find the equation of the curve which passes through the point 1, 2. So we know that when x is 1, y is 2. Has a gradient function given by this. So to go back and work out what y was, I'm going to use my little rule then. I'm going to go along term by term, just like we do with our differentiation. Increase the power by 1. I'd have to then divide by that new power, so I'm going to write 1/3 dividing by 3 at the front, and you can check backwards always. So if I differentiate a third x cubed, I would get back to x squared. Increase the power by 1, divide by the new power, so we get a half at the front. 2 must have come from 2x, and there's a possible plus c on the end. Now when they give you some more information, when they give you a point that the graph goes through, then we can work out what c is. So if I replace y with 2 and x with 1, then I can actually work out what I get for c. And it turns out that c is equal to 1/6. So there's my equation. So we know that if we've got dy by dx equals 2x, then we know that y equals x squared plus c. But there's another way of writing that using integration notation. And the notation is like a long curly s. That means integrate, or find the integral of. So if I wanted to integrate 2x we then also have this bit on the end, dx, which actually just means in terms of x, or in with relation to x. But we must always have it. So the answer to that, of course, is x squared plus c. So if we look at these examples, integrating 3 dx means integrate 3 in terms of x. Well, that must have been 3x plus c. Whereas if we're going to use a different letter, then we're going to have a different d something. So this one's integrate 3t dt, because we're working in terms of t. So t goes to t squared, and we divide by 2. There's already a 3 at the front. 3 over 2 t squared plus c. If I want to use the notation here, I want to integrate this whole expression. I'm going to put it all in a bracket with the dx at the end, integrate all of that in terms of x, or with respect to x. And so again, go along term by term. And that's what we would get. So in general then, if we're starting with integrating a x to the power of n, a is just a constant, then we're always going to increase the power by 1. Sorry, that should be an x. Increase the power by 1, so it goes to n plus 1. And divide by the new power. So whatever number is at the front just stays there. And we get this. Is this true for every possible value of n? Well, again, you might like to just pause this for a moment and have a think about that. Well, it does work for pretty much every value of n. The only one where it doesn't work is if you try to integrate x to the power of minus 1. Because if we follow the rule here, we increase the power to 0, we're going to be dividing by 0. And we say, hang on a minute, something isn't right here. So it works for all values of x, except x equals minus 1. And we will learn more about what we do in that situation later in the course. Now the rules then are exactly the same as they were for differentiation. So if I want to integrate something like this, I'm going to rewrite it first and then apply the rules. This one I'm going to rewrite as x to the half. So we can do this with negatives and fractions as well. Increase by 1, it goes up to 3 over 2. Divide by 3 over 2, that's the same as multiplying by 2/3. This one, cube root of x is x to the 3rd. Rewrite this one as 3x to the minus a half. And integrate all of that. I'm doing this quite quickly, but you can think about it in your own time. And just make sure you can see how I'm getting these answers. This one I'm going to expand the brackets and then integrate. And this last one, I'm going to actually do the dividing by x cubed. Rewrite it using power, negative powers, and then integrate. Okay, and then last two examples. Find y, which is this integral here, and find c when x is minus 1, y is 1. So if we integrate, we're going to get 2x cubed minus x squared plus c. We're going to plug in those values. Therefore we get c equals 4, and so y equals 2x cubed minus x squared plus 4. And then finally, if dy by dx equals 4x minus 12, the minimum y value is 16, use the gradient function to find the value of x at the minimum point. Well, we know that minimum points are where the gradient is 0. So we want to solve this equation, x equals 3. And so we know that the minimum must be at the point 3, 16. They gave us the y value at that point. Find the equation of the curve. Well, I'm going to have to integrate 4x minus 12. So that's going to give me 2x squared minus 12x plus c. So there's my equation. If I plug in the values that we've then got from this point, then again I can work out what I get for c. So c works out to be 34, and therefore we get y equals 2x squared minus 12x plus 34. Okay, so then you've got some questions to practice down here. Now these are all taken from Cognity section 5.5. So once you've done them, you can go on there, see if you can find where they are, and you can have a look at the answers. You can even mark them yourself, which would be great. Okay, good luck.